Well, here we go for the review for Math 13 final. So this data right here is real data collected. This is the balance that people had on their credit card, Visa card, and this is their age, and of course we also have their gender. The first thing that I'm going to do is type the data into the calculator, and to save some time, I've actually done that already because I'm sure you don't want to just sit here and watch me type numbers in. So in list 1 and list 2, I have the balance in list 1, the age in list 2. So this is in list 1, this is list 2, just as a reminder. And then on to the first question. So the first question is using a 2x2 contingency table. We're testing the claim that a person's gender and their balance are independent. In other words, the balance that somebody has on their credit card has nothing to do with their gender. Okay, so with gender, it's pretty clear how I'm going to divide that male and female. And the data is already divided the males and then the females. But for balance, I then have to choose what number to put here to say those that have less than this balance and those that have bigger than or equal to this balance. And you can't just randomly choose that number. It has to be a number that basically divides the data 50-50. So the best number to do that would be the median. So just as a quick reminder, it's list 1 that has the balances. So now I'm going to find the mean and standard deviation for list 1. And if I scroll down just a little bit, it'll also tell me the median, 624. So that's the number I'm going to use. Those that have less than 624 and those that have bigger than or equal to 624 for their credit card balance. Okay, so now what I need to do is go and what I'm going to do is I'm going to highlight or put a little check mark by all those that have less than 624. So just looking at all the balances, if they have less than 624, put some type of mark or highlight by all of those. It has to be less than 624. Oh, here's a good question. This one is exactly 624. When I made this up, I said this is going to be less than 624 and this is bigger than or equal to. It really doesn't matter where you put the equals, but I decided to put it on that side. So this is strictly less than 624. So this 624 right now does not count as less than 624. So in total, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 people. And if I just look at this again, so there's 35 people total and 17 of them have less than 624. So that's pretty much half. Now that means that when I add up this square and this square, it's going to be a grand total of 17 people. Next, I have to put the males that have less than 624 in this box. So right here's the dividing line between males and females. So for males less than 624, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. And now in this box will be the females that owe less than 624. So that would be these females, 1, 2, 3, 4, 5, 6, 7, 8. And then notice that the 9 and the 8 does add up to 17. So now I don't need this 17 anymore. Okay, next are going to be the males that owe bigger than or equal to 624. So that's going to be the ones that do not have a check mark. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 males O bigger than or equal to 624. And finally, the females that O bigger than or equal to $624. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, before I move on, I want to make sure that I counted everybody. And of course, I could look through the list again and make sure, but I could also look at, again, the sample size is 35. And if I add up these 4 squares, it should also equal 35. Okay, so everybody got counted, nobody got double counted. We're ready for the next part. When you make this contingency table, you should leave some space in here because at the end I need to fill in the expected values in these little spaces. And one guiding principle or one rule is all of these expected values need to be over 5. If they're not over 5, then I actually chose the 624 incorrectly. But this, by choosing 624, this is 17 people and this is 18 people. So that pretty much split it 50-50. So I'm pretty sure all the expected values are going to be just fine. Next, enter this as a matrix. So you go to second matrix, then over to edit, choose matrix A. This is a 2x2 contingency table. There's some old numbers left over from another problem. That's fine, just type over those. 9, enter, 10, enter, 8, and 8. So there's our table, 9, 10, 8, 8. Next, go to the chi-squared test. So stat, tests, and then chi-squared. The one that just says chi-squared test. Next, it's going to say matrix A and matrix B, which you should just leave that alone. That's the default that should be already set in the calculator. And then go to calculate. It's going to tell us the test statistic and degrees of freedom. So now I'm going to draw a little picture of the chi-squared distribution. This particular test is a right-tailed test only, so we're using 95% level of confidence. That means it's going to be 0.05 on the right, and degrees of freedom is 1. And the chi-squared is table A4. So to look up the critical value, this is table A4, and right here is 0.05. So this table, in case you don't remember, this table is split down the middle. These are the right tail test critical values, and this would be left tail. So this is right tail with 0.05. It said degrees of freedom is 1. So that means this is the critical value, which says 3.841. So the critical value is 3.841. And then the test statistic, chi-squared, is equal to 0.024. And this basically lands way over to the left, not even close to reject, which is basically the test's way of saying, you know what, as far as gender and how much people owe, there really isn't a difference. Now, officially, we would say fail to reject the claim, or in other words, we did not prove anything here. So we did not, what it's really saying is we did not find a difference between someone's gender and their balance. But it seems that people's gender has nothing to do with their balance. And if you look at the females are split pretty evenly 8-8, the males are split almost evenly 9-10, so there really isn't a difference. Okay, then on to the next one. So this one, we're going to now break it up by age. Those that are the youngest, less than or equal to 25, those that are middle, 26 to 49 years old, and then those that are over 50. Now, separating the data here is probably the most challenging part of this problem. So first of all, I need to highlight these people, the very youngest. So you could go through with a highlighter, or you could use check marks or whatever. And this is going to be the people that are under 25. So I would highlight them. That person's 19. This person is 24. This person is 19. This person is 22, etc. Notice that I'm highlighting all the way across because the question is actually about the balance on their Visa card. So I'm using their age to put them in different categories, but then the question is going to be about how much they owe on their Visa card. So just go through and highlight, and to save some time, I already did all of the highlighting. So in yellow, I highlighted everybody that was under 25 years old. So you can see all of these ones highlighted in yellow are the younger people, under 25. Then in red, if they were ages 26 to 49, so this person, etc. So I highlighted all those red. And then in black, I highlighted all those people that are over 50. Now the next thing is type their different balances into lists. So into one list would go these yellow balances, 235, 122, 0, 84, etc. Into a second list would go these red balances, 1655, 355, etc. And then finally in a third list would go the balances for these that were highlighted in black, 1752, 1543, etc. And again, to save time, I already typed these in the calculator. So this is the list of balances for the younger people. This is the list for the ones that I highlighted red. You can see it starts with that first red one, 1655. And then these are the older people. Their balances, 1752, 1543, etc. Okay, once all of that highlighting and typing the information in the lists is done, then we're ready to do the next part. So the next part is find the mean and standard deviation for each group. So these are the younger people in list 1. Find the mean and standard deviation for list 1. So there are 8 of the younger people. They owe an average of 167.375 with an S of 155.224. Next, stat calculate the one variable statistics for list 2. So that is 16 people. The average balance is 1531.063, going to 3 decimal places, and S is 1994.901. And finally, for the third group, so stat calculate one variable statistics for list 3. So there are 11 of those people. Their average is 2183.818, and the standard deviation 2330.543. Okay, so one thing is you have to make sure that this makes sense. So it's about how much they owe on their Visa card. So does it make sense that somebody owes $167? Yes. Does it make sense that somebody owes $1531? Yes. Often what happens on this particular type of problem is I'll go to grade it, and right here someone will say 20.3. and this will say 31.5, and this will say 53.2. In other words, they typed in the ages instead of the balances on the Visa. So this, yeah, somebody owing $2,183 on a Visa, that's believable. All right, the next thing is the claim is that the three means are the same. So on all problems, make sure that you write down the claim. And with the ANOVA, you don't have to write down H sub O or H sub 1, it's just the claim. Next, it's going to be an F test, and it's right-tailed only, so it's going to look like the last picture. And F test is table A5. There's degrees of freedom number 1, and there's degrees of freedom number 2. And all of this can be done on the calculator. So I have the data in list 1, list 2, and list 3. Then go to stat, tests, and the ANOVA is the last one. Then just tell it which lists your data is in, list 1, comma, list 2, comma, list 3. And it will tell you the test statistic as well as the degrees of freedom. So the F is the test statistic, which I'll just write down right now. F equals 2.686 if I round it to 3 decimals. This is degrees of freedom number 1. And then this is degrees of freedom number 2. And just ignore everything in between. Ignore error and the MS. So this is degrees of freedom number 2. So next, use table A5. And table A5 looks like this. With table A5, you have to make sure that the picture matches with what we have, which this one does. And then the 2 degrees of freedom are 2 and then 32. So the first one is 2, so we're going to be using this column. And then move down to where it says 32. And they don't actually have a 32, so the best that we can do is use the 30. So that's going to be using this critical value right here, 3.3158. 3.3158, and then just right here I actually had to use 30 because that's all they have. And then this 2.6 would land over to the right a little bit, but it does not go past 3.3158. So that means that this one has also failed to reject. Which means that we did not prove anything. Now, in case there's some problem at the end that says give an explanation, notice that there is a difference. Owing $2,000 on a credit card is definitely different than owing $167, but there is such huge variation here and such huge variation here that you can't predict with accuracy that in general, yes, one group owes more. This is close to this critical value, but it didn't quite make it. With it being close, what the test is saying, yeah, I'm starting to pick up on a difference, but you don't quite have enough evidence to prove it. Now, maybe if this would have been 80 people and 160 people and 110 people, that would be enough evidence to prove a difference. But with this, we got failed to reject. All right, on to the next one. So next is part C. See if there's a linear correlation. So age and the amount on the Visa card are the two variables. And if you go back to when I originally typed in the data, so this is how much they owe on the Visa, and this is their age. So I typed it in that the balance was first and the age was second. That's perfectly fine, but just keep in mind that whatever's in the first list is considered X, whatever's in the second list is considered Y. So that means that the balance is considered X and the ages are considered Y. Okay, now linear correlation. So using list 1 and list 2, you go to stat, calculate the linear regression for list 1 and list 2. And it says a few things. One, it gives us the equation of the line. So I'm going to go ahead and write that down. Y equals 0.003x plus 35.591. And the other thing is the test statistic R is equal to 0.305. So R equals 0.305 is the test statistic. And now use table A6 to look up the critical value. For table A6, you need to know what the sample size is. And if I just do the mean and standard deviation again, it will tell me the sample size is 35. So n equals 35. And then use table A6, which looks like this. We're going to be using this column for 95% level of confidence, and then look for a sample size of 35, which they happen to have right here. And then the critical value is 0.335. So right here would be a 0.335 as a critical value. And on the other side, it would be negative 0.335. Then you compare, where does this 0.305 land compared to this 0.335? So it would be a little bit smaller than it. It would land right about here. And when it lands in the middle, that means that we did not prove anything. It was close, much like the last one, but it didn't prove it. So this one is that there's no linear correlation. All right, then for the other part, predict the balance for somebody that's 30 years old. This is sort of a two-part problem because if there was a linear correlation, then you're allowed to use this equation. And if we're going to use this equation, we would have to say, okay, years old, first of all, age means y. That means that this is saying y is equal to 30. Then I would substitute a 30 right here and do 2 steps of algebra to solve for x. But since there's no linear correlation, that means you should not even be using this equation. Instead, to predict what somebody owes on their credit card, you just use the average. So, going back to the calculator, I just found the mean and standard deviation. The average that people owe on credit card is $14.24 and 63 cents. So then the other would be for a 30-year-old, I predict they would owe somewhere around $1,424 and 63 cents. Next up, compare the men and the women. So if you go back to the list of data, and by now your list of data might start to look like this. It's sort of messy. It might look like this, which is a little bit cluttered. So I will have extra ones during the final. You could come up and get an extra data sheet if you want to start over. So this is comparing the men and the women and how much they owe on the visa. Well, it's actually already in order, so I don't think I really need a new one, because this is for the men, and then this is for the women. So I need to put the men's visa balances in one list, the women's visa balances in a second list. And again, so that you don't have to watch me type numbers into a calculator, I already did that. So right here, there's the men. You can see it starts off with 235, 122, etc. And then for the women, I have that in list 4. So you can see the women start with 601 and then 56 and 452. Okay, Next up, find the mean and standard deviation. So list 3 is the men, that goes first. So stat, calculate one variable statistics for list 3. This is going to be the information for the men. So the sample size is 19. The average that men owe is 1536.895. And the S, 2389.602. Then for the women. So that's list 4. And there are 16 women. The average is 1291.063, and S is equal to 1415.055. Okay, then for the claim. So the claim would be that the two means are equal. And I'm going to call this group number 1 and this group number 2. So the average for the men equals the average for the women. And then this would have H1, which would be that they're not equal. That makes it a two-tailed test. And then H sub O is always that they're equal. And when we're testing claims about means, it's going to be a t-test, which looks like the normal distribution using table A3. It's a two-tailed test. This would be 0.025 and this would be 0.025 because we're using 95% level of confidence. And in order to use table A3, we have to have degrees of freedom. So in this particular test, degrees of freedom is n-1 for the smaller group. So it's going to be 15. Okay, now on to table A3. So we're going to be using this column right here, two tails, 0.05, and then degrees of freedom is 15. So this column with degrees of freedom 15 is 2.131. 2.131. And then the t-test. So the test statistic will be t, and it needs to be the two-sample t-test. So two-sample t-test would be this one. And you can either use data and just tell the calculator which lists you're using, or you can use stats and then type in the mean and standard deviation yourself. I'd rather just use the data, tell it it's list 3 and list 4. This should be not equals because that is what this is for. Pooled is always no, and then calculate. So the test statistic turns out to be a 0.377. So that would land somewhere in the middle, which means once again, fail to reject, we did not prove anything. Next, party, test the claim that the majority. So the majority means over 50%. So the claim is that it's over, the P or the percentage is over 50%. That means that H1 would be the same. That makes this a right-tailed test. And then H sub O always has equals. Now in order to test this, you need to know the sample size, which I remember from a while ago, is 35. Or you could look right here, the men plus the women, that equals 35. So the sample size is 35. Now for this part, if they owe at least $1,000. So now I just have to go and count how many people owe at least $1,000. Okay, so how am I going to keep track? I'll circle them. If they owe at least $1,000, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let me just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that would be x equals 13. And so p hat would be 13 out of 35. Then when you're testing claims about proportions, it's going to be a z-test. And this one is right tail only. So we're going to be using table A2. And on table A2, I actually need to know what's on the left side. So if the right side is 5%, then this is 95%. And when you look for 95%, you will find there's a tie right here. The little arrow down at the bottom says if you were looking for 95%, the critical value is 1.645. So the critical value, 1.645. Okay, then one proportion z-test. And for this, you just have to tell it what number is in the claim or what number is in H sub O, so that's a 50%. X was 13 people, so 13 people out of 35 people. This is pointing to the right, and then calculate, and the test statistic turns out to be a negative 1.521. So z equals negative 1.521, which actually lands to the left, which means that this should have been set up as a left-tailed test, but that's the way that I asked the question. It was set up as a right-tailed test, so just have to go with it. Anyway, even if this was on the left side, it still wouldn't make it pass, so it's yet again failed to reject. We didn't prove anything. Okay, then on to the next part, which is the conclusion. So based on these, what can you conclude? Well, if you look back at the test that we've done so far, we've gotten a whole lot of fail to reject. Fail to reject. But then again, this one was a 0, which basically means there's no difference between males and females. With this, we weren't able to prove it, but you could see the younger people owe less, the older people owe more. And if you put that together with this one, almost prove that there's a correlation between age and balance, which then would have meant the older people owe more, younger people owe less. So on this one, I would say something like, it seems, I didn't prove it, but it seems like younger people owe less and older people owe more. Though we couldn't actually prove it because we only had 35 people. And if you look at this test, this is almost a 0. So there's almost 0 difference between the genders. And then that's what this one also showed. As far as gender, there's pretty much no difference. So you could comment on that as well. Okay, so that is the one that uses all the data. And now on to questions from earlier in the semester. So out of n equals 1,210 people, x is equal to 117 of them said that they approve of the job that Congress is doing. Now make the confidence interval. So p hat would be 117 out of 1,210. 117 out of 1210. So that would be 9.7%, or 0.097 as a decimal. And then what? Make a confidence interval. So the confidence interval means that the true proportion is between what and what. So you could use stat, move over to test, move down to intervals, and look for the one proportion, z interval. Then you just need to tell it how many successes, 117, out of how many people total, 1210. The directions said use a 95% confidence interval, so this is all set up, and then calculate. So it is between 0.08 and 0.113. 0.08 and 0.113. And then just make sure there's not any other explanation we're supposed to do. That's it. Make the interval. So this is a fact that 19.8% of Americans smoke cigarettes. If 25 were chosen, what's the probability? So what's the probability? That is way back at the beginning of the semester when we were doing binomial probabilities. So we're going to be using the binomial formula. And for the binomial formula, you need to know what the P is, or in other words, the probability of a success, what the sample size is, and then this is saying at most 5. So X is at most 5 means less than or equal to 5. So in other words, there could be X equals 0 smokers, or 1, or 2, or 3, or 4, or 5. So we'll need to do the binomial formula 6 times. But of course, the calculator will do it for us. So you go to second distributions and then scroll down to the binomial probability distribution formula. The number of trials was 25 people, 0.196, 0.198 of them smoke, and then for the X value, start at 0. So this probability would be 0.004. And then you could just go back and say redo this with a 1. And this one would be 0.025, etc. Or if you do that whole thing and you just don't tell it what to put for X, you just put the N and the P, then it will do all of the possibilities. Save some time. So 0.004, 0.025, 0.074, 0.139, 0.189, and then move over. The next one is 0.196. And now just add these together. Add all of those cases. So 0.196 and 189. Sorry, off the screen. And 139 and 0.074, 0.025, and 0.004. So it would be 62.7%, or if you prefer the decimal, there we go. This one is pretty much just a one-word answer. So sampling methods, that was way back in chapter 2, I think it was. That was a while ago. So people are divided by hair color, and 12 are chosen from each group. So this is when you take the population, you divide it into groups, and then you choose some here, choose some here, choose some here, choose some here. This is called stratified sampling. And then that's it. No other explanation required. Next, true or false. So at least 95% of the scores are within 2 standard deviations of the mean. This is true, but only if there's a normal distribution. If there's not a normal distribution, this is false. So if it's ever false, then it's false. Anytime the test statistic is close to 1, you could accept the claim as true. Well, that we had an example of over here on number 1. The test statistic was very, very small. Since it didn't go past this, the rule is you say fail to reject, we did not prove anything. I can't say that it's true. So no, that's not true either. Is it possible to prove that 2 population means are equal? Well, we did one of those right here. And the answer is basically the same. This was very close to 0, but that doesn't mean that we proved these 2 groups are equal. All that we can conclude is we didn't prove anything. Because basically this test is trying to see, is there a difference? If they're approximately the same, it doesn't prove it. So, no. The mean of all sample standard deviations is equal to the overall standard deviation. So, these 2 questions right here basically go back to when you take samples of size n, the z-score would not just be the score minus the mean divided by the standard deviation. You would have to divide by the square root of n. So that means that the standard deviation is actually going to get smaller because you're dividing by the square root of n. So the mean of all sample standard deviations, is it equal to the overall? No, because it got divided by the square root of n. So this is false. The mean of all sample means is equal to the overall mean. That's true. The average of the averages equals the average. Then this was also way back in chapter 2. The 98th percentile means you got 98% questions right. This is not true. If you're in the 98th percentile, so let's say that you took this really challenging chemistry test and you were in the top 2%. In other words, you were at the 98th percentile. You're like, yes, I'm right at the top 2%. But it was a really hard test where the very top score was 56%. And you happen to get 55%, so you're in second place. Well, nevertheless, you didn't get 98% right. So this is just relative to the rest of the class, how did you do, not what percent did you get on the test. Can you prove that smoking causes cancer? No. Statistics can prove there is a relationship. You can prove that there is a higher likelihood to come down with cancer if you smoke a lot, but it can't prove that it actually causes cancer. Normal distributions are made from histograms. Well, histograms are bar graphs like this. A normal distribution is like this. And to say that one is made from the other is not true because they do not fit each other perfectly. The answer is no. And then this also is an example of this. So I made up these true-false questions based on misconception I've seen students have in the past, and I'm trying to correct it. But anyway, with this one, this is very small. Then you just have fail to reject. We're not able to prove anything. So it doesn't mean that you could prove that 2 things are independent. No, all you can say is fail to reject. And then on to, hey, is this the last page already? Wow, this went fast. So this is also from the beginning of the semester. So first of all, I'm going to type these numbers in. So this one I did not type in ahead of time, so you're going to get to watch me type in the numbers. So let me just clear out. That's fine. Okay, so 19 and 21. Oops. This should be a 26, and then 51, 39, and 17. Okay, find what? Find the age of the person at the 33rd percentile. So for one thing, I need to know how many people there are. And I'm probably going to need to know the mean and standard deviation at some point, so I might as well find that. There are 19 people in this list. So the n equals 19 people, and this question is basically saying if you go 33% of the way through that list, which person is that? So 33% of 19 people would be the 6.27th person. And of course, there's either the 6th person or there's the 7th person. There is no 6.27. So you round this up and you need to find the 7th person in the list, or the 7th score. And they do need to be in order. So you can have the calculator do that if you just go to sort in ascending order, list 1. Now when you look at the list, they're in order. And I need to know who is the 7th person. So this then shows the 7th person is 20 years old, or the 7th score is 20. That would be the person at the 33rd percentile. Find the mean and the median. Well, I just did that. So stat, calculate the one variable statistics. There's the mean. So the mean is 25.368, and the median, if you just scroll down, the median is right here, 23 years old. Now create a frequency table with 3 classes. So first of all, you take the oldest person, and since I have these in order, I can take a look at the list. The youngest person is 17, the oldest person is 51. So you subtract their ages, 51 minus 17, and then divide that into 3 equal classes. And what I'm making right now is called the width. So 51 minus 17 gets divided by 3. It's 11 1/3. But I don't want to use a decimal. So instead of using 11.333, then round up, I'm going to use 12. Now to make the table, you start with the very smallest score, which was a 17, and then add on 12. So this would be 29, add on 12 again, and then this would be 41. So this one must go up to 28 years old because this starts at 29 years old. This would go to 40 years old, and then this one has to include the very oldest person, which was 51 years old. Now it's just a matter of counting. So count how many people are 17 to 28. You look at the list, they're already in order, so 17 to 28 would be all of these people up to that person right there, that 26-year-old. And that is 16 people. Next, for the people that are 29 to 40, so this is one person. That's it, just that one person. And then the people in their 40s up to 51. So that would be this person, 1, 2, that's it. Then that one's done. Next, assuming that there's a normal distribution means use the normal distribution like this, where the mean has to go in the middle, and I have the mean right here, 25.368. Then find the probability that a person is at least 21. So 21 would be over here, and then at least 21 is asking for this right side. So the next thing to do is find z. So 21 minus 25.368 gets divided by the standard deviation. That part I didn't write down earlier, so I need to find the standard deviation again. The S would be 9.453. Okay, so calculate this. 21 minus 25.368 gets divided by standard deviation. The z turns out to be negative 0.46. So with z-scores, we only use 2 decimals. And then I need to use table 8.2. So this is back in chapter 6. So now looking up a negative 0.46. So negative 0.4 would be right here. The column for 6 would be right here. So that is right here, which says 0.3228. Now that means that this side is 0.3228. Then this would be 1 minus that. And then that would be the final answer for that. So 1 minus 0.3228 is 0.677, or if you wanted to, 67.7%. Now make a confidence interval for the average age. So 98% confidence interval. That is going to be a t interval. Passed it up, there it is. The t interval. And again, you could use the data and just tell the calculator use list 1, or you could use the stats and type in the mean and standard deviation. Oh, calculator already has it right there. Great. The only thing I need to change is it's supposed to be a 98% confidence level. So we get that the mean is between 19.833 and 30.904. And then the last part is a brief explanation. So I'm 98% sure, because we use this, the average age of students at Hartnell is between, and then you just put those two numbers, 19.833 and 30.904. All right, that's it. That was fast.